Hello chemists. In this brief video we're going to give a short overview to Module 5 and the content for your embalming chemistry course. So in this module you see that we've got quite a lot of videos, and it's much more intensive this time on watching videos than on readings. So make sure that you're ready to take notes on the videos as you watch them, pause them, repeat, go back as many times through those as you need to. So let's go ahead and take a look at what we're doing in the term. So one of the things that we're going to discover here is that the molecules you studied before have some interesting properties. Inside of a molecule are atoms, of course, and not all of those atoms are created equal. Some atoms are greedier for electrons in a bond than others. So when two atoms are participating in a bond, the atom that has the highest electronegativity is the one that wins that tug of war for more electrons. So they're still sharing electrons. It is a covalent bond, but the property of the bond can shift based on which kinds of atoms are involved. So this term called electronegativity is a value that we can map, and you see here an image of a periodic table that has the electronegativity values posted. The important thing to note here is those atoms that are bright red in this table are oxygen, fluorine, and chlorine. Those are our most electronegative atoms. So if we see and nitrogen and bromine are also quite electronegative. So if we see those atoms participating in a bond and present in a molecule, we have a clue that we have an electronegative atom. And that means that this bond is going to be called a polar bond, most likely. So if we have covalent bonds within a molecule that are polar, it happens because there's a difference, a big difference in electronegativity values between one of the atoms and the other. So let's look at a couple of examples. So for instance, here's an example of oxygen, O2. Each of those atoms is highly electronegative, yes, but there's no difference between them. So even though they're electronegative atoms, it's a nonpolar molecule. Contrast that with hydrofluoric acid, HF. Fluorine is highly electronegative. Hydrogen is not, has a really low score, so that's polar bond. If we look at carbon and hydrogen and methane, that CH bond is nonpolar because the electronegativities of carbon and hydrogen are very similar. So a little bit different, but not different enough to be called polar. If we look instead at water with its bonds between hydrogen and oxygen, each of those covalent bonds will be polar because oxygen is very electronegative and hydrogen is not. So when we find a polar bond, it happens because we have a big difference in electronegativity between the two atoms, and the atom with the higher electronegativity is pulling those electrons more toward itself. So just a couple more examples here. Chlorine, those two chlorine atoms are highly electronegative, but because they're bonded to each other themselves with the same electronegativity, it's a nonpolar bond. Hydrochloric acid, very different electronegativities. Yes, that's a polar bond. Sodium chloride is in fact so different that we have an ionic bond. So that's kind of the extreme where the electrons pulled so much towards chlorine that they actually ripped them away from sodium. So in this unit, we're going to be talking about covalent bonds and polar covalent bonds. So those polar bonds in a molecule can turn into a polar molecule. So any molecule that's polar has to have polar bonds, right? That kind of makes sense. But once you've got a molecule, there's a little bit of geometry that happens that could make things with polar bonds be nonpolar. So I made you a flow chart so that you can kind of walk through that. So go ahead and test any molecule against this flow chart. There's also a Quizlet so that you can practice assigning whether bonds are polar and molecules are polar. So work through that, get confident in your skills, go through the homework assigned in the readings and do those practice problems, and then you'll be ready to complete a quiz on polar bonds and polar molecules. The other part of the course is looking at why polar bonds are important and why polar molecules are important. The reason they're important is a polar molecule behaves very differently from a nonpolar molecule. And that leads to large-scale consequences in things like solubility and solutions. We're going to be working on that in Module 5. To the shapes of proteins, whether something is a solid or a liquid or a gas, all of those things are affected by the fact that a molecule is polar or nonpolar. You'll have a chance to practice that with some really cool interactive tools that we've got embedded in Module 5. So the other thing to note, because of this difference in polar molecules, is that the attractions between molecules are different if they're polar and nonpolar. Again, you'll play with some tools to experience that for yourself. But just a couple of vocabulary items here. One is that all molecules have electrons and protons, and so they are all eligible for a kind of intermolecular attraction called a London dispersion force. Beyond that, once we see that we've gone from nonpolar bonds to polar bonds, we see that molecules start to be eligible for attractions with other polar molecules. And we call these dipole-dipole forces. So an example that's drawn here is hydrochloric acid molecule, HCl. The hydrogen atom is bonded to the chlorine atom. The chlorine has that high electronegativity, so it's drawing electrons to itself. And in this view here, we can see that it's got this little delta minus. So that squiggle is the Greek letter delta, and it's minus because electrons are negatively charged. That leaves hydrogen a little bit electron poor, so we give it a sign delta plus. So that plus minus notation helps us see how molecules can interact with other molecules. Just like opposites attract with ionic compounds, and just like opposites attract with the poles on a magnet, we've got pluses and minuses attracting, and of course minuses and minuses would be repelling. So there's actually a subcategory of dipole-dipole force that's so strong it has a special name, and that name is hydrogen bond. So if we have OH and the H atom is attracted through space to another oxygen attached to an H, that's called a hydrogen bond. So that is eligible when we've got OF and N attached to H. So why is this important? Why are we digging into looking at intermolecular forces and things like solubility? Well, it turns out that solubility is going to be really important for you when you're doing embalming and some of the consequences of solubility. So just for example, here's a collection of embalming molecules. These are all polar. We see lots of CO and OH bonds here. Red is oxygen, white is hydrogen. The green here is chlorine. So these are all very polar molecules and they're very water soluble. So when you get to embalming, you're going to have some physical consequences of solubility. One of those is, of course, dissolving these compounds into water so that you can use them. But the other one is that it turns out you're going to be using solubility to look at osmosis. And that's important if you're embalming a body that happens to be dehydrated or bloated, and you've got some tools at your disposal with solutions in order to accomplish a good embalming. So just a quick vocabulary lesson. A solution is composed of a solvent, which is the bulk of the solution, and a solute, which is the stuff that's dissolved in the solvent. So we need those terms together so that we can look at osmosis. So in osmosis, there's a definition, right? And the definition of osmosis is that we're looking at how a solvent molecule moves across a membrane in order to equalize the concentration of solute on both sides of that membrane. So there's sometimes easier to explain this with an image. So there's a little cartoon here. In the cartoon, we've got a black dashed line that represents the membrane. And the membrane, what is that? It's a cell membrane. So it could be tissues, it could be blood cells, any kind of cell within the human body. And the red spheres are the solutes, and these are things like dissolved sugars, alcohol, could be salts, right? All of the things that are dissolved inside of a human body. And then the blue dots spheres represent water molecules. So in this example, we've got on the right-hand side 6 solutes, 6 red spheres. And that's a higher concentration than on the left where we've got 2 and a little bit of 1 peeking in there. So that means that there's a driving force for the water molecules to move across that membrane and get the concentration of the solute equal on both sides. The solute's too big to move across, so water can move across the membrane. So that's how osmosis works. And again, it's a driving force to make the concentrations the same on both sides of the membrane. So you'll have some great videos to watch about how this works, and they'll include some good animations. And then you'll encounter this vocabulary of hypertonic solutions, isotonic solutions, and hypotonic solutions. The other thing you're going to do is the last assignment, and you can learn more about the assignments in the assignment videos, but you're going to be choosing a lab activity that helps you illustrate osmosis. So you can choose either to do a carrot lab, where a carrot is simulating a body, and you'll explore what happens with that carrot when it's in hypotonic, hypertonic, or isotonic solutions. Or you can do a computer animation, and it's totally up to you. We actually use the same grading rubric for both of those activities, but it's up to you. The only thing about the carrot one is make sure that you give yourself a couple of days, because once you start it, you need to come back and measure again 1 day later, and then measure again 2 days later. So you'll need a couple of days ahead of time to plan for that carrot activity. It's not difficult, it just takes a little bit of time. So I highly recommend that one. That would be my preference as a chemist. So have a good week this week. I hope that you will reach out for help in the inbox or in discussions and attend office hours. Don't suffer alone. If you're stuck and you need a little help, please do reach out and get that help. We're happy to help. So good luck with Module 5 this week.